At the start of the 20th century, astronomy operated within a limited but internally consistent picture. Observations were confined to optical wavelengths. Distance measurements extended only across the Milky Way. Stars were treated as the primary constituents of the universe, and the structure of space itself was not considered a variable. That picture changed through measurement. In the 1920s, Edwin Hubble measured distances to faint, extended objects, then labeled nebulae. He used Cepheid variable stars, whose intrinsic brightness follows a well-defined period-luminosity relation, to estimate distances. The results placed these objects far beyond the boundaries of the Milky Way, at distances of millions of light-years. They were separate galaxies. Hubble then compared those distances with spectroscopic redshifts. The relationship was systematic. Galaxies farther from Earth exhibited larger redshifts. The pattern was isotropic. Direction did not matter. Distance and recession velocity were proportional. The interpretation followed directly. Space itself was expanding. At the time, this result did not destabilize existing theory. General relativity permits solutions in which space-time evolves. A universe emerging from a denser state would naturally expand. Under known physics, expansion governed by matter and radiation should slow over time. Gravitational attraction between all mass energy acts to reduce expansion velocity. This expectation followed directly from the equations. It also matched classical reasoning. Systems dominated by attractive forces decelerate. The unresolved quantity was the rate of deceleration, not its existence. For several decades, this assumption remained in place. Distance measurements carried large uncertainties. Observational coverage was limited. Expansion was treated as an initial condition whose future behavior could be refined as data improved. By the mid-20th century, cosmic expansion was considered established. Gravity was assumed to control its long-term evolution. The remaining work focused on parameter estimation. At that stage, there was no recognized inconsistency. By the late 20th century, cosmology entered a phase defined by precision measurement. Improvements in telescope sensitivity, detector linearity, and statistical analysis allowed direct tests of assumptions that had previously been adopted without verification. One such assumption concerned deceleration. To measure changes in the expansion rate, astronomers required distance indicators visible across large fractions of cosmic history. Type 1a supernovae provided such a tool. These events occur when a white dwarf approaches a critical mass and undergoes a thermonuclear explosion. Their peak luminosities show limited intrinsic variation and can be standardized through light curve calibration. In the 1990s, two independent teams used Type 1a supernovae to compare distances with redshift across billions of years. The objective was to measure how much cosmic expansion had slowed due to gravitational attraction. The data showed the opposite trend. Distant supernovae appeared fainter than predicted in decelerating models. The discrepancy increased with redshift. Extensive checks were performed. Dust extinction, selection bias, calibration errors, and evolutionary effects were examined. Independent datasets produced consistent results. The expansion rate in the past was lower than the expansion rate measured more recently. This implied acceleration. Within general relativity, a universe containing only matter and radiation cannot accelerate its expansion. Acceleration requires a component with sufficiently negative pressure to overcome gravitational attraction on large scales. No such component was present in the standard cosmological framework. The result persisted under further observation.
Additional supernovae surveys, baryon acoustic oscillation measurements, and large-scale structure studies reinforced the conclusion. In 2011, the observational discovery was awarded the Nobel Prize in Physics. From that point forward, cosmic expansion no longer followed the behavior gravity alone predicts.
Once acceleration was established, cosmological models required modification. The equations governing expansion relate geometry to energy content. To produce acceleration, an additional contribution was introduced. This term carried energy density and pressure values chosen to match observations. It was labeled dark energy. The term does not correspond to a detected particle, field, or interaction. It represents an inferred component, defined solely by its gravitational effect on large-scale expansion. When included, models reproduce supernova distances, cosmic microwave background observations, and galaxy clustering statistics within measured uncertainty. Current data indicate that dark energy contributes approximately 68 to 72% of the total energy density of the universe. Ordinary baryonic matter contributes about 5%. Dark matter contributes roughly 25%, inferred independently through gravitational effects on galaxies and clusters. Dark energy lacks such independent confirmation. Its properties are not measured locally. Its presence is inferred from the expansion history alone. The terminology reflects this status. Dark denotes the absence of direct detection. Energy refers only to dimensional consistency within the equations. Within the models, dark energy resolves the discrepancy in expansion behavior. It does not identify a physical mechanism. After acceleration was incorporated into cosmology, attention shifted to determining the present expansion rate. This rate is expressed by the Hubble constant, typically given in kilometers per second per megaparsec. In principle, this value should be unique. In practice, it is not. One measurement approach uses the nearby universe. Distances to stars are determined through parallax. Those distances calibrate Cepheid variables. Cepheids calibrate supernovae. The resulting distance ladder yields a present-day expansion rate based on local observations. A second approach relies on the cosmic microwave background. Measurements of temperature fluctuations at redshift approximately 1100 are fitted to a cosmological model. Under assumptions about the universe's composition and evolution, the current expansion rate is inferred. Both methods achieve percent-level precision. Their results differ by several kilometers per second per megaparsec. The discrepancy exceeds combined statistical and systematic uncertainties. The difference has increased as measurements have improved. Independent instruments, analysis pipelines, and observational strategies reproduce the same separation. This disagreement is known as the Hubble tension. Its significance lies in consistency. If both measurements are correct, then the standard cosmological model does not describe expansion accurately across time. Either early universe physics, late universe physics, or the connection between them is mischaracterized. There is no accepted resolution. The tension persists across experiments. At present, the universe's expansion rate depends on how it is measured. Cosmic expansion cannot be studied experimentally. There is no method to manipulate space-time, adjust its energy content, or repeat its evolution under controlled conditions. Cosmology relies entirely on observation, constrained by light travel time and causal structure. Every measurement samples the past. Reconstructing expansion history requires assumptions about continuity and dynamics between observational epochs. Phenomena affecting expansion operate at extremely low energy densities. Their effects are undetectable in laboratories, particle accelerators, or solar system tests. They emerge only when averaged over volumes spanning billions of light-years. This creates a structural limitation. The dominant component of the universe influences global behavior while remaining inaccessible to direct testing. Models can be adjusted to match observations. Confirming the mechanisms behind those adjustments requires evidence that cannot be obtained. After decades of observation, the situation remains unchanged. Expansion is observed. Acceleration is measured. The present rate depends on method. The cause remains unidentified. These are not gaps due to insufficient instrumentation. They reflect limits imposed by scale, causality, and observational access. The universe is expanding faster, and the reason is not known.